let me know when everyone's ready to start. So I'm here to tell you about functions. This is a functional meetup, right? So do you know how functions work? Like when you compile our code and it's a lot faster than Python, it might be as fast as C, or sometimes faster, when you're not crying about concurrency, do you know how your functions work? OK, cool. Well, I can maybe help you fix a little bit of that. And I don't mean fixed point. So there's sort of two goals of this talk as one. So most of the slides are actually going to be sort of with like a little toy lambda calculus and me grossly abusing Edward Kemet's bound library, which is really nice for actually dealing with variables and stuff. The first half of this talk is going to be sort of nearly, you could just modify a little bit and actually have it be working code, walking through closure conversion and CPS translation, and sort of motivating those a little bit, because the way you're often taught to, when you're first learning a functional language, you're sort of taught the algebraic substitution model for how computation happens. And that's not really what happens. So I'm going to sort of sketch that out in a gross abuse of half a talk, and then sort of switch over to briefly outline how function calls work very precisely when you actually get to them, and then give you a lot of code demos and benchmarks. OK, so this is a diagram of GHC. OK, this is everything going on. It's also, GHC is really well written considering it's, that too. No, they have their own compiler for parsing. Or is AMP some build tool? I don't remember. Anyways, so like, there's a lot of stuff going on in GHC. I'm not going to tell you anything about optimization.
Is that available online somewhere?
Yes, this is. So I don't have links in the slide deck right now, but I'll add them before Gershom puts them public, or at least he'll yell at me until I do. So there's a lot of work going on in GHC. So at the start, we start like with parsing, and then like once you figure out, oh, you shouldn't have tabs enabled on your editor, you then sort of figure out how to get things past the type checker. And then a lot of things are reduced into a language called core. If you squint really hard, you'll see this says desugar. And then there's a lot of simplification and optimization inlining going on. And there's a lot of other things, then it goes to core, then to STG. Now, let me actually move forward. Here's where I'm focusing. I'm only even touching a subset of this. So core, you know, a lot of great optimization happens at that level. Usually when you're debugging performance for Haskell code, you might ask it to dump or pretty print core to understand what's going on in terms of all the Haskell level internal PrimOps. And then it's convert to STG, and STG is sort of a further restricted sort of simple lambda calculus. And have you ever heard of C++? OK, cool. So it's not like C++.
It only differs by a sign.
You know, so C++ actually is its own separate language. Like if you go to c-minus.org, there's like a little compiler just for C++. GHC has its own implementation of C++. Also, by default, the type checker is turned off for C++ representation. When you're debugging the compiler, you want the type checker for C++ turned on, but it's kind of like an untyped C that doesn't understand when any pointer arithmetic will be at the byte size. So you always have to remember to do that. But it's basically everything right before we do LVM or native code generation, or I mean, this dot part of the diagram is old. There's no F via C anymore, so ignore that part. But so how does code get to C++? So the first half of this talk is actually going to be me on what are the non-optimization, the totally unoptimized stick figure versions of the transformations that let us go from Haskell, core Haskell, down to C++. So evaluation strategy, you know, I'm going to actually be using an example evaluator that does the inefficient form of normal order evaluation, which is laziness without the cleverness. So it's called normal order evaluation. And so you may have seen it in the previous slides, a mention of ANF. ANF is administrative normal form, also known as monadic normal form. And it is sort of just basically explicitly naming every intermediate value and having nice linear nesting to these declarations. CPS, I'll sort of derive in a really cute way from wanting to actually, with like this toy interpreter language, you can actually, and I'll be a little bit hand-wavy, but you can actually derive CPS from writing an interpreter where you are not using the host language stack. And I'll actually introduce closure conversion first, which is how functions are values instead of just pointers, at least in compiled code. So all the examples are, with a little bit of work, they're not pseudocode, they're actual working code. And I'm using this really great library by Edward Kemet that I only finally understood properly in the last week, that really makes it easy to deal with variable binding in a nice, really well thought out way when you're writing your own little programming language. So here's the brief punchline of the cleverness with bound. So we have E, let's just make up some notation. E, what we have is we have some type language, some data type M for a language. And the type for variables in this sort of data type is going to be A. And we have free variables, as I see over here, type A. And a substitution, when we're evaluating code, when we reach a variable, when we're writing an interpreter, we usually go look up in the environment. So that's a mapping from variables to some sort of value or concrete language expression. Likewise, so when we are then traversing a data, doing a substitution, it's just we're applying that function all over. And so substitution over all subexpressions looks exactly like monadic bind. And in fact, it is an instance of monad. So whenever you see monadic bind, actually just think recursively substitute. OK? Yes. So here's a little, this is a sort of a literate slide deck. Well, not quite, because I changed definitions in subsequent slide decks to sort of augment things in interesting ways. So this is just some prelude stuff. OK, so let's just have an abstract syntax tree. So expression of type A, we have a variable of type, some sort of variable of type A, which we have function application, and we have lambda abstraction. Ignore this part this scope black magic for now. It's not really essential to the talk, but it is sort of part of the machinery for handling binders in the bound library, and it's really nice. And this is some more nice boilerplate, just so it's all working code. This is I'm actually building all these examples, modifying the simplest example in the Kemet bound library. So how do we define that substitution, that monadic bind? So we're substituting, we're applying a substitution to a variable A. So we just apply that sort of mapping, and we look up a value. Either it acts as the identity, and we just get a new VA, or we actually replace it with a lambda or something else. With function application, we just recursively pass the substitution down forwards. And then when we have a lambda expression, we do something that looks like a bind, but looks like the bind, but has an extra character. The point is, it sort of is, it's the bind, but working on that scope thing that I used to define the lambda data type. You can also do some nice shorthand, like defining your own lambda abstractions. And again, the abstract one part is another nice little thing for handling the variable substitution in the bound library. So here's a toy evaluator for normal order evaluation for the simple untyped lambda calculus. Normal order evaluation, when things terminate, this will terminate. It's the only one that's guaranteed to kind of terminate. And it's not efficient because there's none of the sharing that you see with lazy evaluation. And so what's going on here? When we have a function application, we're saying, hey, if we have a lambda, apply it. Do a substitution of the value to the variable that's implicitly captured by this lambda. Otherwise, just return the application of something that's not a lambda that we can't reduce to a lambda to just an application. And anything else, we just return it. So what next? So let's modify this a little bit, because functions are values. And when we're writing a practical compiler, we're not copying and pasting all the variables we compute into the sub-expressions and then recompiling it, unless we're using Common Lisp and we're doing some crazy runtime stuff. Or some of the stuff some of the code I might be writing later this summer. But you shouldn't normally do it unless you have a really good reason. So what am I doing? Oh, well, remember I was just saying substitution or environment is just like a mapping? I'm just saying, a closure captures the substitution at its defining point, and the way we'll actually, and I'll actually see how we implement that in our evaluator. So I changed the monadic thing to actually say, when we're doing a substitution, we just turn to a closure. And when we try and do a substitution on a closure, we just return the closure, because it's already closed over. Closures close. They don't accept any substitutes. I was so proud of myself when I came up with that sentence. So here's a little, so the lambda case in our evaluator actually is no longer valid if we do a top-level identity substitution. That is, we're closing over the free variables in our code. So I'm just saying, create a closure where we don't actually replace anything. But, and okay, this doesn't quite type check as is, but bear with me. It would be like lift m or whatever. Yeah. So that's actually not type check. But the idea is still there. Do like the identity monadic lift on any lambdas on everything you encounter. So that means any top-level lambdas we'll encounter will turn into closures. And then, but we won't substitute below until we actually evaluate them. Let's look at that a little bit. So we have application, and we're not actually doing this case anymore. What we're doing is we're saying, hey, evaluate that f until we get a lambda, if applicable. Well, no, we'll actually get a closure. But then what we do is we apply the substitution when we're applying the closure. We don't actually substitute into the sub-expressions until then. And the lambda one is still there for comparison. OK, so
that doesn't obey the monad laws, I guess.
Which doesn't?
E bind ID.
Well, yeah, I said it didn't type check. This is, it is A to A. It needs to be A to MA. So this was just, I said it was pseudocode that you could just modify slightly. Yes, good call. I did define return a few slides back, so good catch. Well, it's actually the example from the bound library. This isn't a very interesting interpreter. It totally leans on the host language for every feature and capability ever. Like this, we're using the Haskell stack to do our recursion in this little lambda calculus. It'd be cool to actually, modify our evaluator so that we have an explicit stack, because that happens if you want to compile your code eventually. So what we need is like let's go back one slide and look at this. Look at the original evaluator. I have a non-tail call usage of the weak head normal form function over here in the case expression. Is everyone with me there? Okay. And then, once that normalizes, which maybe might take a while or could go for longer, if I actually wrote this as a strict normalizer, by that I mean forever. And then once we're done normalizing f, we go back and eventually do this function application. That's where we have a non-tail call application of our evaluator. So what I want is I actually want to sort of have an explicit stack, right? So I'm actually saying, sorry, okay, hang on. Screen temperature at night. Is that better? Yes. forgot about, okay, and you know, that's a good thing to know. Okay. So I kind of want, when I did that little recursive step, to have a little bit of context saved that I can eventually work back to. Okay? So maybe what we want is we want a evaluator that, you know, we give it the current expression, we give it the current stack of steps to do, and then we return something, return a new expression that is going to be normalized in some sense. Okay? So this is also kind of a, aside from normal ASTs, this is actually the first time I've written a function type where I had a recursive type. So I'm kind of proud of this. Like I wanted to actually like motivate via stack machine getting to CPS, and you know this is kind of neat. So the idea, this is actually a function always. It's just I can always pull out a new function that I can use, has this exact same interface from this list over here. Okay? Does everyone get that trick? Who's confused? I know at least one person's confused. I'm totally mindfucked the first time I saw this sort of stuff. There's basically the reason why it's not like, wait, why isn't it? So what you might be wondering is, why isn't this an infinite type? Like, if I just write down the function, it'll be like really big arrows or something. Like, is that kind of what your confusion is? What's your confusion? No, it's okay to be confused. Seriously, it's confusing. Don't.
Those of us who don't know Haskell are not confused at all.
I must be doing something right. Is that the more method?
No, that's an okay type. Maybe, right?
So the more method is working.
What's that?
The more method.
Yes.
Excellent. You may be also noticing that I'm actually just writing down like little recursive equations as pseudocode, but with a little bit of fixing that little id cock. Laziness to write a compositional library? Oh no, there's no actual computation going here. It's just saying this is so I could totally write this without any confusion in any untyped language. I just say, oh, there's a list of functions here. What I'm saying more precisely is it's the exact same shape function as these. So it's, you know, it's not that, it's a little bit non-obvious the first time you have to do it, but then you're like, oh, that's cool. So here's the version, the explicit stack machine eval, or weak head normal form. So let's look at this. So first I'm just having like a little apply, where I apply the stack. I'm not applying normal functions. I'm saying, if I have an empty top level and I'm not doing an evaluation step, if I'm done, I'm not calling this initially, I should just return that value because it's already normalized. If I have a little machine here, I should actually apply that, unwrap the top machine, and apply it to the current expression with the rest of the contexts. So this is sort of you actually see this in sort of what are called, if you read any PLT papers that talk about the evaluation strategy of their languages, you'll see big step operational semantics with contexts. And I'm actually just making that context explicit as a little function. So now let's look at the sort of eval part, or like the normalizer. And I had to sort of butcher the layout to make it fit on a slide. But at least this is the most complicated slide I'll show you, I swear. Now, in function application, I'm saying, oh, normalize the function argument, and here's the context I want you to go to next once you can no longer recur downwards and normalize. But in the meantime, it's just going to keep on powering through until it hits a non-application case. And then it's going to apply a context and then sort of eval from there. So the context I'm creating here is saying, hey, and this is the constructor saying, hey, it's this funny recursive type, is that, you know, okay, you give me an expression, I case over it, and if it's a closure, I can just actually, you know, I do an application to like do this substitution downwards. Yes?
So your stack at this point is basically, in some sense, a stack of this is where to return
Yes, it's a literal program stack as part of the interpreter. Every Haskell style function here, except for this instantiate one, which doesn't really count, I swear, is all in tail call position, right? Is anyone confused about that claim? Or does everyone buy that by me having the loudspeaker voice? Is every function I wrote aside from instantiate in tail position here? Really? I didn't hear that many people. That confuses me. I need more people anyone confused by this? Or is this really, really obvious? It's really, really, what? Okay, cool. Okay. But the point being, I'm not using the Haskell stack at all, except for with this instantiate thing, which is kind of like saying, which doesn't really, let's gloss over that for now. It's basically unpacking a closure and installing it on the stack is kind of what that's doing if we were to view it as a compiler. Okay, so point being, I do a normalization. If I can do further reduction because we have a closure, I do normalization there with the rest of the contexts. Or I just do the stack apply to sort of return this value into the next context up. Well, this is, it would be even easier if I didn't have to write a weird-looking little interpreter like that and just had all that context stuff baked into the language. So that's what CPS translation is. It's instead of doing this, which also looks a little bit code golfy on a slide, we want to actually have the stack be part of the linguistic structure of the language. And it would be kind of cool because if you expose the stack as sort of using one of the built-in programmatic constructs, what you can really do is you can optimize you can optimize away stack allocation. A naive compiler will actually sort of every time you have a function call or step, it'll have a lot of little stack activity, especially a functional one. But by actually having all the stack allocation explicit as a linguistic construct, you can optimize a lot of that away because you have registers. You can use them. Okay, so partly because I didn't know how long getting through this first half would take, here is CPS. So what's going on here? Let me walk through this. So we have a top-level expression, and we have a top-level continuation, which in the previous two slides ago was an empty list. Does everyone remember that? Vaguely. Cool. Okay, so when we have an expression that's an application, we want to first, and actually this is the call by value CPS, I guess, which is different from the evaluation strategy we were doing in the previous slides, which was more normal order. But that doesn't really matter because this is like a short talk anyways. Well, long short talk. So we have a top-level continuation, and then first I want this guy to be in. So if we were doing this, so let's pretend that this was setting interpret or evaluate instead of to CPS. Well, if I wanted to do a function application, I first have to evaluate E1, right? Yes or no, right? Yes. Okay. Cool. So and then there's something we're going to return to, K. Well, so we should first sort of do a CPS of this guy with it being passed a continuation argument given the value that we get from evaluating this, we then sort of evaluate, and this is because it's strict rather than the lazy evaluation strategy from before of the argument. And then we just actually resolve that to apply v1 to v2. And we've modified the lambda to always take an extra continuation parameter. This is, of course, grossly unoptimized. But it gets the job done. And so then when you have a lambda, yes, so a lambda is also a value. So we apply the current continuation, and then we have a new continuation in here where we CPS the internal expression, and we have the parameter that we're threading down. And otherwise, for some variable, for this simple lambda house, we just do kv. Okay?
How do you decompose a lambda like that?
Oh, this was just pseudocode. This is really, really pseudocode. So this slide is not real Haskell, if anyone thought that. Sorry. I just wanted to actually make it really, really straightforward, because otherwise I wasn't sure how much time I would have left for talking about the other really dirty low-level bits. I don't know what this bullet point was for. Oh, well, there's a lot of really great, there's a lot of great work, beautiful work on CPS translations, and I'm horrified that I've just done one slide and kind of motivate it through a stack machine interpreter. But I wanted to make it clear that CPS sort of removes a bit of complexity in terms of reasoning about the stack from the implementation itself, because up to some modulo some amount of engineering, it makes the stack explicit. What you can actually, in fact, do is, instead of using a normal syntactic lambda for continuations, you have a special k lambda for every time you have a continuation lambda function, or a k closure for the continuation closure. And then you optimize a bunch of those away, and because you don't need to do all those load stores. And then any k lambdas or k closures you have left are where you do stack allocation. The closures where I just said, oh, we just save this monadic function we're applying, are, it tells us which things to save on the stack, or load onto the stack, or load into registers. And when we do a function application where we have v1, v2, and k, as I just showed here, all the way in the corner over here where the syntax highlighting breaks, that the environment being captured that is still live in that continuation is the stuff we need to save when we enter the function call, okay? Which is kind of cool. I'm happy to explain more while we're drinking. I actually talk about more technical stuff later, as everyone who deals with me knows. But okay, so this is the end of this. Well, so again, to remind you, C minus minus, it's actually kind of a C without types, as horrifying as that may sound. You can turn on the type checker, but it's not on by default. It's CPS, it's continuation passing styled, and it's also closure converted, because it's kind of like C, where you just have pointers. And so we actually need to understand, so I kind of just gave you that whole mini talk about CPS and closure conversion just to explain this slide. C minus minus, you have basic blocks that are essentially your lambdas that are sort of mushed together because enough to use registers and whatnot effectively. And then you're always just doing a tail call with possibly some explicit stack allocation as determined by the continuation you'll be going to later. And then you just sort of jump, and I'll get into this a little bit more. So how do function calls work at the C minus minus level? So GHC has its own calling convention. And to quote a friend of mine who is starting some work on LLVM soon, it's kind of weird compared with most other calling conventions on the LLVM. Most calling conventions for LLVM, if you actually take a look at them, I'll show you the GHC one. It's really simple. It's actually kind of a declarative specification. Actually have explicit, beyond the first few arguments, push onto the stack. That isn't exposed as part of LLVM, although it's done partly because it's all done on the Haskell side for its own calling convention. So I'm going to be talking about the calling convention that is precisely true for 7.6 and also 7.4. I read the source for both. It's the same. So you have 6 registers assigned for words. You have 3 registers for base, heap, and stack. OK, so 4 registers. I can't count. 2 SIMD registers for doubles and 4 SIMD registers for floats. In GHC 7.8 or current head, all 4 of these first SIMD registers you can use freely for doubles, floats, or sort of SIMD vectors. Although it only looks like there's planned support for SSE for 128-bit style registers for now, although AVEX style 256-bit stuff is in order. Anyways, so after these arguments, any more arguments, they're just put on the stack, and there's some pretty readable code in the GHC compiler that I will include a link to in the finalized version of these slides that sort of you can read to figure that out. So what are these fixed registers? So base goes into this Intel. So this is only for 64-bit Intel compatible CPU instruction sets. And God bless you if you somehow, yeah, well, you'll always have the SIMD registers. So you have stack pointer at this register. Don't worry if you don't remember. You won't remember these later. It's OK. It's really easy to look up if you ever actually care. And usually you won't. So these are the 6 ones for words or pointers. And then for floats, they are put into these 4 registers, which is a little bit of those guys can fit 4 floats each, and we're only putting 1. It's a good thing SIMD's coming to GHC, and it's already landed in head. And then we have 2 for doubles, and then that's it. But OK, here's actually the specification in the actual LLVM source code for this calling convention. It doesn't reflect the version I was telling you where specific SIMD registers are reserved for floats versus doubles, but it does accurately reflect the precise structure of which arguments will be passed in registers. So let's walk through this. So any 8-bit or 16-bit or 32-bit thing is just considered 64-bit. It's, so what? You could hypothetically fit 4 8-bit things into a 64-bit thing. No, I'm bad at math. 8. 8-bit things. So this is like a nice, so if it's one of these types, consider it to be 64-bit. This is STG is the spineless tagless G machine. Gershon was alluding to this earlier. STG is sort of a low-level graph reduction substitution model for a lazy functional language. It's just you can turn it into things that look suspiciously like C. And then, so you'll see float 32-bit, float 64-bit, and then these guys are things that you can actually use as normal Haskell values-ish come GHC head if you can figure out how to compile it now, or this fall. There's also a few other cool things coming to GHC this fall, like a JavaScript backend. I'm really excited about that one too. OK, so and these are spilled to the stack if you don't have SSE. This is all. There should be some work at some point to allow using the AVEX extension, which doubles the width of SIMD. But honestly, that doesn't matter. So why on earth would you use like C++ instead of C or Haskell? Maybe you want to write some low-level code and do multiple return values and interact with the runtime system. Maybe you want to allocate on the stack. Maybe you want to mess with the heap. Maybe you're writing new concurrency PrimOps. Or maybe you like writing things that are kind of give you all the error handling support of assembly. It's also kind of fast. It's just it's more low level than C, and Clang has better error messages, a lot better. At least when. So actually now I'm going to show you a bunch of code I wrote where I wrote a Haskell version. I wrote a C++ version. I used a trick courtesy of the alpha heavy folks, specifically Nathan Howell, that lets you write C code and then you mangle the calling convention via LLVM so it uses the Haskell calling convention. You can just link to it as C++ code. And also some C code that you just call like normal, using the normal CFFI. OK? Who wants to see this? OK. OK, there was another slide. So references, I'll add those later. OK? OK, so first let me note that I too use Sublime, even though I'm not on Windows. So let me just first show you, here's the code here's the code I haven't shown you yet that I'm going to benchmark. So I benchmarked, oh, yeah. OK, how do I do that? OK, well, I'm making the font really big. I'm not sure if that's the same thing. OK, is that readable-ish? OK, that's more readable, sorry. OK, so basically there's 2 things I'm benchmarking. Computing the factorial of, these are micro benchmarks. These are not interesting benchmarks, but I think they're very illustrative and helpful for having a first step comparison. So I have some really cool SIMD code I've written for other purposes, and for those purposes, the C code will win. But this is just to actually measure the overhead of transitioning between Haskell and something else. This is not actually meant to illustrate anything else. So first, let's go through. So I have add a number to itself, and then I have factorial. Okay? So remember how there's like the R1 through 6 on that slide deck? Or would you like me to remind you? So if you use GHC head or pending 7.8, when you write C minus minus, you can actually like have like int arg1 blah blah blah. But with current C minus minus, it's actually you have to explicitly unpack anything from the stack, and you're given arguments R1 through R6 for integer or word-like things, and you are then also have F1 through F4 for float-like things, and D1 and D2 for double-like things. It's actually a good thing that they're switching to having explicit arguments with 7.6 because of the change in the calling convention that lets you have a flexible number of floats or doubles using the first 6 SIMD registers, because otherwise it would be really hard to do this. So what I'm doing here is I include C-minus-minus.h. You really need to include that if you want to use write C-minus-minus code. So I'm just here saying, just in their own internal notation, initialize a variable arg. And then I'm setting arg to R1. Then I'm also setting arg to arg plus itself. I'm doubling the number. That's what I said I'm benchmarking as one of my micro benchmarks. And then I'm returning it. There's a whole bunch of different return macros, and I still don't probably understand them correctly. But I think n means number, because there's also a version that says p that's pointer. I'm pretty sure it means pointer. Nothing crashed, so it's probably OK. So let me also walk through the C minus minus code I just wrote. So what we have here is I have some arg and accumulator, and I'm setting arg to that first argument. I'm also setting accum to that to that same value. Then arg gets decreased, and yes, OK, this is correct. I just read it backwards. So you have go-tos in C minus minus. You're not supposed to use go-tos in C, but you really should in C minus minus, because I don't think there's a while loop or for loop. And function calls are expensive, right? No, they aren't. But they're not. It's a lot of work to do those well in C minus minus. Well, no, you can actually write something like if you actually look at the GHC source code, you'll see stuff like ccall, some sort of function name, and then some arg list as like jumping out and calling some C code that's part of the runtime system. And so this is just basically computing factorial with a little go-to loop. And then, wait, did I? OK. Yes. OK, sorry. Let me just indent this to make it less confusing. OK, there. The return 0 only is happening if yes, it's only happening in the true branch of arg is less than or equal to 0. OK, cool. So that's some C minus minus code. Now let me show you the corresponding Haskell code I wrote. OK? OK, cool. Where did I write it? This is not pretty Haskell code. OK, so I actually wrote 2 versions of the Haskell code. OK, so I first had a version where I said, OK, cool. So is this readable for people? OK, so this is just a thing. So I'm using the excellent criterion library to do benchmarking, and I'll show you. I'll actually run a benchmark run for you in a moment. But so I wrote 2 versions of each Haskell function. One where I said inline me, and this one said don't inline me, because GHC is really good at inlining it. It makes stuff fast. So if you say you can't inline this, I mean, okay, there's actually some times where you actually don't want to inline stuff because it does make stuff slower, but usually the default is inline lots of things and they simplify away, and then you have straight line code that's really nice, and you have really pretty assembly. And so that's what this inline pragma you're seeing here, or no inline. Okay. So first I have the no inline version of add two numbers, and then and factorial, which is I wrote in worker wrapper style. Then I wrote sort of the same thing where I said inline me, seriously, inline me. When you write the inline pragma, it says inline me. You are required to, unless I'm recursively calling myself, in which case you'll like say fuck you. You know, it's you know, you don't want to inline recursive functions. It's bad. There's actually GHC has a notion of called loop breakers, which is how it says I can't inline you further, Bob. But you know, that's okay. So does everyone kind of see like I wrote the same code twice, but it kind of makes sense? Well, it's okay. I already compiled it, so if I mess it up, it's okay. So what you see here. So let's see. Where do I? So let's see. Okay, so here's the C minus code. I did foreign import prim, and then the quoted name of the actual function, and then I gave it the function, the name I want to expose, and its type. And you might see some hash marks at the end, right? Can people see those hash marks? Okay, cool. So that's called a unlifted type, and you can't use type classes with things that end in hash marks because they're the unlifted, sort of fully inlined, no boxing types that you have the nice pretty ones exposed to you as. You actually never have a good reason to use these unless you're doing something like this, because GHC is really good at unboxing and unwrapping sort of the lifted versions of Word and int and whatnot. And I was actually having a funny challenge earlier where I was trying to write Word 64, and I found out that Word 64 is just Word underneath on 64-bit platforms. So there's a funny gotcha from conditional compilation in that there's no explicit Word 64 hash. It's Word, whatever your architecture, Word. Word. So then I wrap it up where I do this little pattern matching thing. And I actually couldn't, so you may notice here I'm reconstructing it with res. I can't actually take this code here and then just put it here. It'll actually complain because it literally, it's it just doesn't get it. It has to be some sort of like, it's like a syntactic restriction on, it has to be something that's already, it can just bang into being an unboxed word. So if you start doing crazy stuff, that's why that's happened. You're getting weird things. You always have to basically do the A and F, the let normal form, or CPS of the computation to actually feed in the word values. That you can't have a thunk. And this is one part, I mean, granted, when I do this is still a thunk. It's just that it gets less confused about that in terms of the syntactic requirement for unlifted types. Likewise, you can't use stuff like the apply $ operator with unlifted types. They will get really unhappy, partly because apply is polymorphic and you can't use polymorphism with unlifted types, which makes sense. So I also wrote some, so here's a few more things. I wrote some normal C code. Notice how it's in normal.c. And I use both the safe and unsafe FFIs. So the safe FFI is the default one if you don't specify which FFI protocol you use. And it actually sort of runs the C code in a separate process and sets that all up and does some isolation. Whereas if you do the unsafe FFI, the capability that's running that code right now can't do anything else until you return. But it's better for writing PrimOps because you don't really want the scheduler to interrupt you in the middle of a tight loop and then wait for you to come back later. Also, the safe API is what you sometimes want to use when you're calling back and forth between C and Haskell, or maybe I'm mixing it up. I think it's that way. Okay, people are nodding, so I'm probably remembering correctly. Okay, you're also seeing something, now if we scroll further, you'll see something I'm calling C4HS. It's not a Haskell brand of explosives. So as I mentioned before, there's a dude named Nathan Howell, and they have a neat hack where you write C code, and then they use Clang and generate LLVM bit code, and then they change the calling convention in the LLVM bit code, and then they just compile and just say, oh, we swear that's a C piece of code. And I'll show you that code in a moment. And then I benchmark all this. So let's look at c4.c. So let me zoom out so remember how I told you about all those registers? Does anyone remember that I said there was like a lot of registers going on and there's a fixed calling convention? Good, okay, that's the important thing. So this is partly cribbed from their example code but modified for the functions I want to run. So what you do is, so you have the base register, and then the stack pointer, and then the heap pointer, and then R1 through R6, and then the stack pointer limit, and then 4 things that we could put floats in, and then 2 doubles. And this is the register-based calling convention. And so how, like when we want to return, okay, cool. I have a little macro, so it's less painful, right? And so then we have, like a little way of actually saying, given a pointer, pretend it's a function that does that. Again, cribbed from the alpha heavy code. And so then we can sort of define, so then given a pointer, we can just say, oh, return to that, and call it, and just put in stuff there. So here's my little double code. And the way I've written it, it's kind of like a more painful version of the C code, actually. So I have those arguments that I didn't really want to write down, named in the exact same way as if you were using C++ code. I'm then actually taking the top pointer from the stack and calling it the function saying it's a function that has that type I told you guys about earlier. I then take the value from that register. Let's ignore the fact that I was sloppy and used signed integers here. Doesn't really matter, it's C. Or assembly or whatever. It's all the same at some point. I extract out that value and I double it, and then I say, oh, do the return for one number like thing, because I'm just copying the naming convention because it's easy. And I say, here, use this, jump to this code location with these things on your arguments. Okay? And so then I have a factorial function. And I kind of do the exact same thing, but I have a little loop for, just while greater than 0, accumulate, subtract the number, and then return accumulate. Okay. So I ran some benchmarks, but let's just run one, right? Let me just build, blah, blah, blah. And I'm running the benchmarks, because I generate a little object file. And I'm now going to open up a very nice little criterion template in a moment that is a modification of the standard criterion template because I wanted a nicer one. And so a friend helped me figure out how to write JavaScript last weekend. It's a weird language. The scoping is so weird. And I say this after giving you this talk. It has weird. I wrote a fucking talk on scoping, and I was confused and had to have friends babysit me to figure out how to write JavaScript code, because scoping was weird. Like, semantically weird. Like, I understand semantics. The first half of this talk wasn't crazy talk, right? It made sense. It was a little bit condensed. JavaScript has weird scoping. Okay, so let's just open the template. Okay, so when you want fast code, takeaway number 1 is when you should never use the safe code if you want fast code. So what I did here is I actually called each function. So it's not rendering the tooltip thing. So this first thing, because I did things 1,000 times, so I have enough sampling resolution, is microseconds, not nanoseconds. Okay, so most of this code for adding 2 numbers together and doing it 1,000 times is on the order of like 5 microseconds, which is not too shabby. That's like you doing the assembly yourself. No assembly required, though. I'm in a punny mood today. So now, so let's look at, so first of all, as I said before, when you do the safe calling convention for C code, it spawns off a separate process and makes it safe, and it doesn't block the scheduler and other nice things like that. So here, I added two numbers, but I said you can't inline. Seriously, you can't. Although LV, and because if it inlined, even though criterion prevents really aggressive inlining, LLVM is really good at doing more. So not inlining at all is worse than calling C code. Okay? So, but if you inline, well, let's see. There's a C minus minus. It kind of looks like the Haskell code was the fastest of all these when I let it get inlined, because the fastest function call is no function call. If only just because branch predictors and pipelining work better when there's no jumps to like runtime determined locations. No, because normally with GHC code, if I actually spent the time to walk you through how the actual function application, generic Haskell level function application works, generically you don't know what the code you're going to jump to is until you do. And criterion is such that you actually are essentially measuring the cost of an unknown jump in terms of the way it's designed. And the fact that the WHNF thing, not in my slides, but in criterion, has a no inline pragma in its definition so that it doesn't get specialized to know what it's actually calling. Because you don't know where you're going to land. So let me better explain. If you have a generic function that's calling another function, I feed it. If you do not know what that function I fed you is, which is by definition the case if I said you can't inline me, you cannot inline me. If you look at the criterion source code, let me just go back to the. No, that's memoization. Memoization is an entire different cost. No, what I'm saying is, I have a generic function. I say you can't inline or specialize it. You can specialize this guy to finer types, but you can't inline the code. It's a higher order function. I feed it a function, it applies it. It can't know what it is unless I inlined it. So like here, you'll see I do weak head normal form iter because I'm measuring things. And over here, I define weak head. It's doing the weak head normal form. And the weak head normal form bit here, there's a no inline pragma in the criterion library. But anyways, so what I'm essentially measuring here, as I was saying, is all of this code where you're doing a tight loop and you're doing a function call. What difference is there in the function call? What difference is there in performance in the function call overhead? So when it's inlined, it kind of gets to cheat because LLVM can be really clever. Oh, the highlighting is working again. Cool. So you can see those little, is it showing? Yes. You can see those little time units, right? Cool. OK. So, and then I did factorial, and they're kind of all the same. So I think the takeaway is, unless you really want to interact with the runtime system, or whether it's, say, pause for a moment and let the scheduler do some stuff, or to allocate memory on the heap, using the CFFI is actually less painful. I might, as a fun hack, sort of cook up a little C preprocessor for C4 that I'm going to call C4HS, but it remains to be seen. Because it kind of looks like unless you're doing a lot of function calls in a tight inner loop, you're not really going to win much from, that's a small gap unless you're doing it like a million times. But even then, it's a small ratio.
Saying NS for the units. What's NS?
Nanoseconds. Yeah, so I'm calling factorial of 10, and these are all the codes. This is the Haskell inline code. This is the Haskell no inline code. Let me just check.
And on top it's microseconds?
Yes, because I did 1,000 times. Because there's not enough timing resolution. I mean, maybe I should have repeated these guys, because this is pretty fast still. And 20 nanoseconds from other experiments I've done is about the timing resolution for criterion. Actually, let's do that right now. It's really easy. Who wants to wait a minute for me to make that change? Sweet. That's because we're in a persistent land. Okay. So this is why higher order functions are good. Making live changes won't not work, usually. So let's do it 1,000 times to get a better separation. I mean, granted, you still have that little loop, but that's not too bad, and LLVM might cheat around it. Okay, so build. Okay, it didn't crash while I was building it. That I had a few. And so we're going to get a little ASCII printout, but I'm going to open the HTML because pretty pictures are sometimes easier to understand. Okay, so now let's go to Finder. Oh, it's still running. Did I break fuck, I broke factorial. This is why version control is important. What did I do? I just indented it. Oh, or was it? Oh, it was actually taking a while. I'm sorry.
You've omitted the safe benchmark for this.
Yes, because it was obviously slow with the micro benchmark.
What source control are you
S-tree, which works with Mercurial or Git, but I'm using Git because I'm lazy and because it works-ish for my one-person version control stuff, and me giving people. That's really slow. Is that a bug?
Do you want to just keep looking at your initial timings for everything?
Oh yeah, good idea.
Go through this?
Okay, so there is some timing difference. Like the unsafe CFI is still slower than everything else. And there's an important caveat to make here. If I have a tight inner loop and I want to shave all the overhead I can, just bring down all the constant factors where there's not like a finite amount of mass, like sort of doing like the trick for doing the LLVM hack, which I can explain. It's a really simple. It's simple. That saves some time, and then you can also use vectorization. And then internally, I could have done if I had a little bit more time, I could have written a nice little simdified version of the factorial code, and actually use that and use some instruction level parallelism, and maybe gotten a sort of a nice 4 to 10x speed up on larger factorials, or doing a large array dot product. I actually have such examples where I am actually faster than the normal Fortran for matrix multiplication. So, if you can do stuff in C that you can't do on the Haskell side currently, involving messing with registers or vectorization intrinsics and straight line code and whatnot, it's worth doing. C++ doesn't yet expose SIMD, but it still lets you do a lot of nice stuff. And you can write more direct style Go2e code. And LLVM apparently is confused by larger CPS basic blocks. And so that sort of gives you a way of working around that without breaking out the compiler toolchain. I can take more questions after, but I think this is about it. Is that still running? Yeah, okay, I broke it. I don't know how. Cool, thank you very much, and I appreciate it.
Hi guys. If you're looking for opportunities to work with or around Haskell, my company SchedgeMe is looking for people to work on the front end right now. So it's a perfect opportunity for someone who is a beginner in Haskell but more experienced in JavaScript. Our back end is pure Haskell. And our front end is pure JavaScript right now. We're always looking for opportunities to do more things in a functional style. So if that's something that might interest you, you should get in touch. We're going to be making a decision for this position next week. So try to get me your resume by the end of this week if you're interested. And if you're interested in Haskell positions, we don't have any open right now, but you might want to send your information along anyway because we are expanding pretty quickly. So we will get in touch with you when a position opens up. My email address is ryan@skedge.me. That's SKEDGE.me. And of course, I'll be going to the bar afterwards, which will be announced in a moment. And you should talk to me there if you're interested. Thanks.
Okay, we have the standard Central Bar after event. It's on 9th Street between 3rd and 4th Avenue. Just walk south on Broadway. East till you get to 9th Street, then east like a block and a half, and it's called Central Bar. Thank you to Pivotal for hosting us here. Leave quickly so they can get back to the things they want to do. Thank you.